First of all, am I audible?
Yeah, you are.
Okay, great. So, uh, Pells equation is an equation of this form where d is an integer, let's say non-zero for now, and d is not a perfect square. So, and we want to solve this over the integers, over integers xy. So, like, for suppose d was a perfect square, then this is like almost trivial, right? Because we can factorize this, and then we have to
Yeah.
check some cases, and we are done. So this thing is not very interesting. So we'll work with d not a perfect square throughout. So can anybody tell me an obvious solution for this?
Oh, plus minus 1
Yeah.
was 0.
So uh, these are like, this is the trivial solution. So let's just ignore this for now, and we'll look for other solutions. So okay, we want to solve something like this. So it turns out that it is good to factorize it like as this. And then uh, we will look at numbers of this form. So let's just make this definition. It will be useful like this. So here by SD, we denote the set of numbers of the form x plus root dy, where x and y are integers. So, uh, can anyone tell me why this set doesn't contain two same numbers? Like, anyone tell me why x plus root dy is x dash plus root dy dash implies and implied by x is x dash, y is y dash?
Just because root d is not an integer, so y prime like root d is not a rational number, so y minus y prime like x minus x prime divided by y prime minus y is a rational number, so root d must be a rational number, but that is a contradiction since we assume that d is not a perfect square.
Yeah, exactly. So good. Uh, so this set has distinct, like, so this is a property that we have. No two of these numbers are the same. Now, uh, we want to solve something like this. So we want to solve over elements of SD something like this. We want to solve over integers this thing, and uh, this motivates, like, somehow we can see that this root dy term and x term are sort of like unrelated, like don't talk to each other. And so let's just define something right now. If z is a real number belonging to SD, which means z is of the form this for integers x and y, then we define the conjugate of z as, like, uh, the most reasonable guess, x minus root dy, if z is x plus root dy. And uh, we want to solve over z belongs to SD, z bar equals 1. Okay, so Now, uh, just like in suppose complex numbers, conjugate has some nice properties. So like uh, conjugate is multiplicative. So like this is true, which is because just because like this is xz plus dyw plus root d times yz, uh yeah, plus xw, and when we take conjugates, notice first that like okay, so conjugation is a well defined notion because like as I said earlier, x plus root dy is like if we have a real number z belongs to Sd, it has a unique representation in this form because of the same thing. Like if two numbers are same, then x is x dash and y is y dash. So conjugation is a well-defined notion over the set this, and again because of that very property, we have that uh, like if we expand this, we get this. Yeah, and if this is z conjugate. This is suppose okay. This is bad notation. Let this be alpha. This be beta. Then this is alpha conjugate. This is beta conjugate. So we have that alpha beta also belongs to St because it has this representation, and hence it has a unique such representation. And similarly, we have alpha bar, beta bar also belongs to St and has this unique particular representation. And moreover, because these representations are unique and the notion of conjugation is well defined, we have this thing. And this is a very important property. So, yeah, conjugation is multiplicative. Now, the main thing we are doing this is because we want to solve Pell's equation. So, let's just think about what x square minus dy square becomes in terms of St if z is an element of St such that z equals x plus root dy. So remember, the whole motivation of this was factorization, like this thing. So so we have that this is actually this is z conjugate. So for each z, we have a number like this, which is well defined again because of that, uh, which is nice, and we call it norm of z. Yeah, which is defined to be x square minus dy square, where x comma y is the unique pair of integers such that x plus root dy is z. Okay, so just because conjugate is multiplicative, we have this other amazing property that norm is also multiplicative. I.e., if we have z1, z2 belonging to Sd, then norm of z1, z2 is just because of the definition. Note that if z1, z2 belong to Sd, then this also belongs to Sd, that we showed earlier. Then norm of z1, z2 is z1, z2, z1 bar, z1, z2 bar, which is because the conjugation is multiplicative, this thing, which is this thing, which is n of z1, n of z2. So we get that this norm thing, which we define, also notice that uh, conjugation was a map from SD to SD. However, norm, okay, like norm also belongs to, like, norm is an integer. Integer. So norm maps SD to Z. Yeah. Okay. So we have that norm is also multiplicative just because conjugation is multiplicative. So any questions till now? Yeah. So if A belongs to SD, provided A is not 0, then 1 by A also belongs to SD. Yeah, that is also true. Let's. Okay, no, wait. Okay, that's not true because just taking A to B, 2 plus root D times 2, 1 by A does is like we can rationalize this is half of 1 by 1 plus root D and 1 minus root D, 1 minus root D, and this is 1 minus root D over uh like 2 times 1 minus D or something. Yeah. So this is of the form Q1 plus root D Q2, where these are not necessarily integers. So yeah. So this is like again with this because of the same thing, 1 by A has a unique representation of this form, so it doesn't necessarily belong to SD. Okay, but we'll see something like this over elements in SD, which are solutions of the Pells equation. So uh, let's not worry about that for now. Okay. Yeah. So yeah. So any questions till now? You can reply at the chat also. No, we don't generally take D to be square free. We can do that, but it isn't necessary. We can also have D to be of the form 2 root 3, like 5 root 7, something, anything. Uh, wait. Why would it want be unique representation? So if D is 2 root 3, suppose, then every element of SD is uniquely written as like this because like of the same argument, right? No, I'm not relating SD1 with SD2 right now. I'm not relating two different Ds. I'm working with a single D. Like, let's fix D for the whole thing. For the whole lecture, let's fix D. Among those, uh, like, by uniqueness, I don't mean that SD are disjoint or something. Like, I just mean that we are working in a single SD, which is a subset of the reals. And in that, every element Z, which belongs in this set, can be uniquely expressed as x plus root d times y. Okay. Okay, yeah, great. Now, yeah, so we want to solve Pell's equation, which is this. And this is, first of all, do you see why if x comma y is a solution, then plus minus x plus minus y, we take anything that is also a solution, just because they square to the same thing. So let's restrict ourselves with positive solution, which I defined as a which I define as okay, wait. A positive solution to x ordered pair of integers is such that to Pell is so that x is greater than 0, y is greater than 0. Both are integers, so naturals, and this thing. Like they satisfy Pell's equation. Okay, so we want to figure out what type of solutions this equation has. So in terms of SD, we want to find Z so that Z times Z conjugate is 1. So suppose I find one such Z. Suppose I find a solution Z which satisfies this. Then do you see why all numbers of the form this, where k is an integer? Okay, no, wait. Let's go for naturals for now. We'll do integers. Yeah. Are also solution to this version of Pell. Note that this version of Pell is same as the previous because of the bijection. Like any element in Z belonging to ST can be uniquely under yeah, that that thing. Yeah. So do you see why plus minus Z power k is also a solution to this? You can type in the set. Like
Yeah.
this is okay. So let me explain anyway. So because norm is multiplicative, we have n of, let's go with, yeah, plus minus 1 into z n time is just n of plus minus 1 is 1. So 1 into n of each of z is 1. Yeah, so it's 1. Now let's go back to that question that somebody asked. Yeah, so 1 by z. So turns out in particular elements z belongs to SD satisfying n of z is 1. They have an inverse inside of SD. To see that, note that first of all these are non-zero, so 1 by z is a well-defined real number, and n of z, n of 1 by z. Okay, no, this is okay, wait. So we don't know 1 by z belongs to SD yet. So first let's show that if z is a plus b root d, then 1 over z as a real number is this, and we rationalize it, a minus b root d, and this is because a comma b satisfied this is just 1, like a square minus db square, which is 1, and this is this. So this indeed does belong to ST, and when it does belong to ST, then we can use multiplicativity to show this, because n of 1 is 1, and as this is 1, this is also 1. So 1 by z is also a solution, and thus we have that 1 by z power k is a natural number, plus minus is also a solution to this version of Pell. And hence, if we get a solution this, then all uh, all solutions, like these are also all solutions where k belongs to integers. Yeah. So okay, so for now let's just assume this thing. Wait. Let's assume this thing. We'll prove this at the end of the lecture, I think, if we have time. Okay. So yeah. So let's just assume there exists some z set which is not 1 plus minus 1 such that n of z is 1. Let's say okay. So yeah, let's just say there exists some z greater than 1 satisfying n of z is 1. Then this corresponds to every z belongs to SD, which is greater than 1, corresponds to a positive solutions of Pell, right? Because z, if z is x plus root d y, this representation is unique. Then if z is greater than 1, then these both must be positive. And that is because if they weren't, if suppose one of those was negative, note that mod x plus root d mod y, this would be among uh, z, z bar. Okay, let's not do that. So, my claim is that if z is greater than 1, then z is equal to, and x z belongs to SD, which is x plus, and thus z is x plus root dy, then my claim is that x is greater than 0 and y is also greater than 0. Now, this is because if suppose, let's say, let's take this case, then z is x minus root d uh, mod of y, like this is minus y, so these are positive. Yeah, and but z also satisfies Pell, so norm of z equals 1. So x minus root d times x plus root d is 1. But that means one of these must be less than 1 and one must be greater than 1. But clearly this is greater than this. So this must be less than 1 and this must be greater than 1, which is a contradiction because we assumed that this was greater than 1. Okay, so now we have this thing that z is equal to greater than 1 corresponds uniquely to an ordered pair. The correspondence is the same, x plus root t y thing, where x is greater than 0 and y is greater than 0. Okay, so for now, we just assume this thing that there exists one such z, and then the nice thing is that we can characterize all such z. So now, assuming there exists one such z, we already saw that if we have a z satisfying nz is 1, then plus minus z power k also satisfies nz is 1. Now, the natural question is, does there exist a sort of fundamental z satisfying this alternate version of Pell? A z belongs to SD, such that all W belong to SD satisfying this alternate version of Pell are of the form this. Moreover, yeah, so turns out that this is true. There does exist a sort of fundamental Z, so that all solutions are of this type. Now
So
note
you're
that,
saying, uh, hello?
yeah,
So you're saying that every solution that is greater than 1 that can be represented as z raised to k for some z greater than 1.
no, there exists a single Z naught. There exists a single Z naught such that all solutions W, let's just write it. There exists Z naught belongs to SD such that uh, comma Z naught is greater than 1 so that for all omega belong to SD, omega and n of omega is 1, we have omega is z naught power k plus minus for some k in integers. Yeah. So does that answer your question?
Okay, right.
Yeah. So First of all, do you guys have any guesses of what we could choose as Z naught? Like, try to compare Z naught with plus minus Z naught power K. Does this, because if we are to claim that these are all the solutions, then this is also a solution. And what property does this have in comparison with all the solutions? Like, do you have a particular guess as to what Z naught might be?
It cannot be perfect power of another Z belonging to SD.
Yeah,
Uh, that's a trivial observation actually, but
yeah, okay. Do you see why, if this were true, then Z naught has the least absolute value among all of these, among all the elements of
yes,
SD?
yes.
Yeah. So let's go with a definition now. Like, we define this. So let Z naught be the minimum number such that Z naught belongs to SD, Z naught greater than 1, and n of Z naught is 1. Now, it is not direct. Okay, so uh, do you see why such a minimum number exists? Assume that there exists one such solution. Like, we are assuming this throughout. Like, we'll prove this in the end. Assume this thing, this. Assume this thing, and now do you see why this is true?
Uh, won't there be a sequence of Z belonging to SD that approaches one?
No. Yeah, there won't.
Okay, so if we prove
You
that there doesn't if there isn't any sequence, then the minimum Z naught is guaranteed.
Yeah. So note that we proved a very nice result above. Yeah. So do you remember that we proved Z greater than 1 if and only if the unique representation uh, of Z as x plus root dy satisfies x is greater than 0, y is greater than 0.
Yes.
Yeah. So can you use this to directly prove that there exists such a minimum?
Okay. Yes. So between any two Z belonging to SD, there is a difference of at least one. So there cannot be a sequence approaching to one. So by, let's say, well ordering property, there must exist a minimum.
Okay. So uh, how do you prove that why is it that the difference between any two such Z is like greater equal 1?
Uh, like for this particular values of Z where X is greater than 0 and Y is greater than 0.
Yeah.
Uh,
Like, I don't think this is true for all elements of SD, but I think this is true for SD intersection Pells solution. Like, this is true for Pells solution. Like, so how about this? That if we determine y greater than 0, then x greater than 0 automatically gets determined.
yes.
Okay. So, and moreover, if y, if we have that z1 z2 are Pell solutions and y1 is less than y2, then automatically x1 less than x2.
Yes.
So if we take the minimum such y, and y belongs to naturals, so by
Yes.
the well ordering
So
property we have a minima, then Do you see why the z naught that we get will also be minimum?
Yes.
Okay, great. So let z not be such a minimum number. Then now let's prove this that uh, all solutions to Pell are of the form plus minus z naught power k for some k belongs to z. So let's first restrict to z greater than 1. So we are trying to show that if z greater than 1 satisfies and z is 1, then z is equal to plus minus z is equal to say z naught power k for some k, yeah, belongs to naturals. Let's show this first and then we'll come to the this result. So like notice that z naught is greater than 1. So consider this z naught square dot dot dot, and these are all solution to Pell. And if we have some solution, like if we show that we can't have a solution in between them strictly, then we would be done, right? Because this sequence becomes large enough after a time. Like the sequence this tends to infinity as n tends to infinity. Okay. Uh, so do you see if we show this we are done? Why?
Yes.
Okay. So
Yeah.
for this, like notice that in SD for solution to Pells, we have that there exists a well-defined notion of 1 by z, which also remains in SD and Pell. Like, let's z not z if so. Can you try to show that if this were true, then there would exist a more smaller solution to Pell, and then we would get a contradiction. So, how about this number? Both of these are solution to Pell. So, this number is also a solution to Pell because reciprocals exists. Like this was shown. I think I showed this, and like this is definitely a real number, and it also belongs to SD because reciprocals exist. So this belongs to SD, and if A B belong, then A into B also belongs. So this power n belongs, and this belongs. And moreover, because of the multiplicativity of norm, we have that this is norm z norm 1 over z times n, and we showed earlier that this thing is also 1. So this would also be a solution, but that is a contradiction because this is greater than 1, and so because of this thing we have this is greater than 1 but less than z naught. Okay, so any doubts in any questions in this, like in this for z is greater than 1, like if z is greater than 1, then z equals z naught power k for some k belongs to naturals. You can type in the chat as well. I'll see it. Okay, great. Now also this implies this result as well because if n of z is 1, then n of z bar is 1, n of minus z is 1, n of minus z bar is also 1, and one of these four numbers must be greater than 1. Do you see? Because just because of the unique representation, like if z is x plus root d y, then one of these four numbers is this. And if z is not equal to plus minus 1, then these both are positive, and hence we have this is of the form z naught power k for naturals, and hence z, let's say if one of these, if one of z bar minus z bar is of this form, then do you see why z is of k in naturals? Z is of this form, k in integers. Note that if z satisfies Pell, then 1 by z is actually z bar, because z bar is norm z is 1. So if say this thing was like minus z bar was this, then we would have z bar is this, the z is 1 over z bar is 1 over this, which is minus z naught minus k, which is indeed of this form. So so this is done. So any questions in this? Okay. So uh, so so up till now we did this. Assume that there exists a solution z naught to this alternate version of Pell greater than d, z naught greater than 1, such that uh, uh, yeah, so till now we assumed that there is one solution, and then we showed that there is this fundamental solution such that this holds, and all solutions to Pells satisfy z is plus minus z naught power k. So this is great. Like we already uh, have done a lot of work. Like almost we have proved, we have found all solution to this equation. So let's do an example. Maybe let's try this. So we want to find all solutions to this. So can anybody tell me how can we find all solutions to this equation?
Yes, there is one observable solution, but like 3 comma 2, x comma y is equal to 3 comma 2. But
Yeah,
how do we
very
prove
good.
that this pair corresponds to z naught?
Yeah, we prove this by showing by bashing for all y less than 2. So
Ah, right. Yes.
let's take y is 0. We don't get x, contradiction. Y is 1, contradiction. So y must be 2, like the minimum value, and for which we get this pair. And I showed earlier that for minimum value of y, this z naught equals 3 plus root 2 times 2 would be the minimum solution to Pell. So all the solutions are of this style. Okay, by k I mean the kth solution. So you'll see what the kth solution means in increasing order. Let's say, and these are positive. Okay, so xk is greater than 0, yk is greater than 0, and these are all the solutions. If we define xk plus root 2 yk to be this, then this gives all the positive solutions. Let's say xk yk gives all positive solutions to Pell. Moreover, notice that we can actually exactly calculate what xk and yk are, because note that the property about conjugation that we uh, like the conjugation is multiplicative. By that, we have that xk minus root 2 yk is the conjugate of this thing above, and this is the conjugate of this power k, because conjugate is multiplicative. So if conjugate of 3 plus 2 root 2 is 3 minus 2 root 2, so conjugate of 3 plus 2 root 2 power k is 3 minus 2 root 2 power k. And from that we have that xk is this thing, and yk is this thing. And note that you can prove that these are actually integers using binomial theorem, for example. Yeah. Okay. So now, yeah. So let's look at a variant of Pell's equation, which is called negative Pell's equation, and this is just this thing. So unlike the Pell's equation, this doesn't necessarily have a solution. For example, this has no solution because taking modulo 3, we see that x square is 2 mod 3, which is a contradiction. So this might not have a solution. So, but if it does, then this also has a sort of fundamental solution z naught, such that where now notice that if norm z naught, like this corresponds, wait, yeah, so this corresponds to norm z is minus 1, because yeah, solution to negative Pells equation. And here we would have that n of z power 2, suppose, would be 1, which is not a solution to negative Pells equation. It is a solution to our original Pells equation. So here it turns out that all solutions are of the form this. Like we take the fundamental solution to be the exactly same definition, like the minimum solution z greater than 1, which is the solution to the negative Pell. We call this the fundamental solution, and then all positive solutions, say, are of the form this. All solutions greater than 1 are of this form. And the proof is very similar. So uh, I'll leave that as an exercise. Okay. So you can try this after the class maybe. Okay. So now uh let's do uh, a problem, I think. Yeah. So uh let's do this problem first. So we want to find all n. Yeah. So you can try this for some time. Uh, so speak up if you have any ideas. Uh, I think I can give you like 5-ish minutes.
First of all, we can prove that n has to be even,
Yeah,
except the trivial solution n equal to 1.
yeah,
That can
exactly.
be proved
So
by modulo 8.
yeah, okay, good. So after, okay, let's say we have that n is even. So let's first do that only. So yeah, so notice that 7 power n plus 1 by 2 is prime, implies this. Now if p is 2, then n is 1. If not, then p is odd. So this is congruent to 2 modulo 8, because every odd square is congruent to 1 modulo 4. So 2 times an odd square is congruent to 2 modulo 8. So 7 power n plus 1 congruent to 2 modulo 8, 7 power n congruent to 1 modulo 8, and this corresponds to n is even, because for odd n, 7 power n corresponds to minus 1, a congruent minus 1 modulo 8, and for even 1. So we have that n is 1 except for n is even except for the case of n is 1. Okay, so we want to solve this. So do you see a Pell sort of equation here?
Yes, negative Pells equation.
Yeah, so this is this. Okay, and we have that this has fundamentals, like we are using this exercise which you can prove. The solution is very similar to uh, the solution for Pell's equation, and for we have that this equation has fundamental solution 1 comma 1, because no shorter value, uh, if y is 0, then we get the trivial solution plus minus 1 0, which we ignored in the first instance. So this is actually the fundamental solution, for which we know that every solution is of this type. Every positive solution, let's say. So we must have that this is equal to, yeah, okay. Now so it is it turns out that it is a very good idea to look at this thing as a whole modulo 7, because this is we have a 7 here. So let's try to work out what this is modulo 7, which means we are trying to work out. Okay, so no, wait, yeah, so this is xk plus root 2 yk, and we are trying to work out each of xk and yk mod 7. Yeah, so we can do this just like, let's say 1 plus root 2 has, let's calculate some initial values. X naught y naught is congruent to 1 1 modulo 7, and x1 is 1 plus root 2 cube, which is 1 plus 2 root 2 plus uh, like you can calculate that this turns out to be 7 plus 5 root 2. Yeah, so this is congruent to 0 and this is congruent to 5 modulo 7. So x1 y1 0 comma 5 modulo 7. Note that if a solution is congruent to another thing, then because these expressions are all algebraic, like we have, yeah, then x1 plus root 2 y1 times x naught plus root 2 y naught squared. This is the same thing as this cubed, this power, no, so yeah, So this is actually x2 plus root 2 y2, right? Because this thing is by our formula this power 2 into 2 plus 1, and this is 2 into 1 plus 1, and x naught plus root 2 y naught is just 1 plus root 2. So we are in each step we are multiplying by 1 plus root 2 whole squared, which is x naught plus y naught root whole squared. So and thus we have x2 is something like x2 is actually equal to x naught x1 plus 2 y naught y1, and these are all remain same under congruences. Like if x naught is congruent to something mod 7, x1 something, y naught something, y1 something, then this whole expression is congruent to uh, that times that plus like yeah, modulo 7. So to figure out, let's say x2 y2, we do like x2 y2 mod 7, which is for which we compute like 1 plus root 2 whole squared times 0 plus 5 root 2, and which is 3 plus 2 root 2 times 5 root 2, which is, yeah, so this is like 20 plus 15 root 2, and modulo 7 this thing is minus 1, modulo 7 this thing is plus 1. So we get, first we get 1 1, then 0 5, then minus 1 1, yeah, and then this times 3 plus 2 root 2 becomes like, let's just do it, 3 plus 2 root 2 times minus 1 plus root 2 becomes minus 3 plus 4, which is like 1, plus 2 root 2 minus 3 minus 2 root 2 plus 3 root 2, which is root 2. So this again becomes this. So modulo 7 working out everything, we get something like this. And notice that after it this it repeats because x n plus root 2 y n is just because of the same reasoning, n minus 1 times x naught plus root 2 y naught whole squared.
So you would get k congruent to 2 modulo in the above expression.
Yeah, so yeah, exactly. So if we were to have that like the xk, if 7 power m comma p is a solution modulo 7 is a solution sorry is a solution to Pells, negative Pells, then this must be suppose xk and yk, for which we get that modulo 7 the first term is 0 if and only if uh, k is congruent to 2 mod 3. Like this is k is 1, this is k is 2, this is k is 3, and so on. And now turns out that if we look modulo 5, which is motivated by this thing, then the exact same, for exact same values of k we get that uh, the yk is divisible by 5. So working that out is like easier. So the first thing is 1 1, then 7 5, and then this is congruent to 2 comma 0. So we do 2 plus, yeah, so 2 plus 0 root 2 times 1 plus root 2 squared, this is 3 plus 2 root 2, and 6 plus 4 root 2, so 1 minus 1, and then After 1 minus 1 we have 1 minus root 2 times 1 plus root 2 squared. This is 3 plus 2 root 2, uh, which becomes minus 1 and minus 1. So after 1 1 we have 7 5, which is 2 0. Let's write it 2 0. After which we have looking modulo 5, like the solution. After which we have this, and after we have negatives, then everything just becomes negative. Minus 1, 1, and then after 6 it repeats itself. So we again get like k is congruent
Again,
to,
yes.
yeah. So for these values of k, the solution, the kth solution to Pell satisfies yk congruent to 0 mod 5, for k congruent to 2 mod 3, and this is this satisfies xk congruent to 0 mod 7 also for k congruent to 2 mod 3, which means that p must be divisible by 5, because this is divisible by 7, and it is divisible by 7 if and only if k is of 2 mod 3 form, and then this thing is divisible by 5. So as p divides 5, we have that p5 equals p, because p is a prime. And so, and that indeed does give us a solution, that if we take n is equal to 2, then p is equal to 5. So we have 1 comma 2 as a solution, and 2 comma 5 as a solution. So any questions in this proof?
What was the motivation of modulo 5?
Yeah, so mm, uh like I don't exactly know, but I think it was because, like, I think this was very clever actually. So you can motivate it by like noticing that 7 comma 5 is a solution. Then a working modulo 7 is pretty motivated, but modulo
Yes.
5, 5, okay, I think it is more sort of motivated by observing that this is a solution. And if we were to classify, like, so because we already have this thing, and if we were to use that p is a prime and solve via Pell's equation, then we must have that, like, if only divisibility by 7 is sufficient, then this must be the case. So it is good to look modulo 5.
Okay.
Okay, so any questions in this particular problem? You can type in the chat as well. Okay. Okay. Okay, so let's do this problem next. And I like, this is actually my favorite problem in 2019 shortlist, and it's very nice. And so uh, I guess I'll give you at least 5 to 6 minutes to, and if you have any idea, speak up, please. Like,
Uh, Sorry to say, but can you read the question once? Some text
okay,
is
yeah.
not clear.
Okay, yeah. So we have a set h uh, a set of positive integers, which is this set I root 2 integer part. Like, yeah, integer part, you know the floor function, right?
Yes.
Yeah. I belongs to naturals, and this is a set of this type. Like, I'm just writing the first few elements for convenience sake. Like this is a subset of naturals, and n is a given positive integers. Then prove that there exists a constant c such that, uh, so consider this set. If we have that a has size more than c root n, like there exists a c for all n. Okay, yeah, sorry, I should have mentioned that. Okay, so prove that there exists c must be before this, I think. Yeah, so prove that there exists c such that for all n, considering this set, if cardinality A is greater or equal C root n, then we must have two elements in A with their difference being in H. So if we have, like, if the size of A is more than root n in some sense, like if the size is about as much as root n, so if A is something like this and its size is more than some constant times root n, then we must have two elements here whose difference is among among this h, which is a subset of naturals. So any doubts, any questions in the uh, problem statement? Hi.
Uh, in the set H, like the I that we are taking in H, those are not congruent to 0 mod.
uh, no, I can be anything. I belongs to integers greater than 0.
Actually, you have skipped 3 and 6. So that's okay. Oh, no, no, sorry. That is the set H. Oh, sorry. I thought that is the set of I.
No, I was just writing the first few values. You can
Yeah,
ignore
sorry.
this. Ignore this. Okay, so uh, I guess I'll give you uh, about 5 minutes from now. And if you have any idea, please speak up. And if you have any questions in between, also please speak up. I will be also checking the chat, so you can message there as well. So, like, uh, we are trying to find, we are trying to prove that there can't exist a very large set A in here. Suppose something like this, so that uh, all its differences are not in H. So, uh, okay, so first forget about H. Uh, what is, can you say that A cannot be very large, but still, uh, like, what about a subset of natural numbers which you can uh, say that A can't be very large and skip all elements of S as its differences? What about a set like, suppose multiples of 3, 3, 6, 9, 12? Can A have, what is the max number of elements A can have so that B minus A doesn't, is not a multiple of 3?
Uh, what can you repeat?
So I said that first let's forget about H for now and let S be the multiples of 3.
Okay.
Then uh, how many elements can A have at most such that B minus A isn't a multiple of 3? Inside of how many elements A can have among these such that B minus A isn't a multiple of 3?
Three
Just
elements.
three.
Yeah. So it can have at most 3 elements. So also in some sense uh, this thing, if we remove the integer part, looks a lot like this because it is integer multiples of something. So if we have like a large thing of this type, if we have a large AP of this type inside of 1 to n, which is also inside H, then what would happen?
Then you can select at most A elements.
Yeah. So no, like not at most A, I think. Yeah, but you can bound it very nicely. Like considering mod A and consider elements of A. Then considering mod A, if there must be at least these many elements which are same elements are same mod A in A in A. So in this set there are at least these many elements which are same mod A. This is by pigeonhole principle. Uh, any questions in this particular thing?
Is the EA that you have written above, EA belongs to H, is EA greater than N or less than N?
less than n. LA.
LA. Oh, sorry.
LA is less than n. So, any questions in this thing? Like,
Is LA the largest multiple of A less than N?
no, it isn't. Like, we are just okay. So, we are just thinking of this. Like, suppose we have some set of this type in H, which is also in this. So, it need not be the largest because it need not be the case that the largest multiple of A in N is also in H. So, we are doing this because we are like this is a huge motivation for what we can do. So we can't, like, in general, exploring what b minus a takes is hard, but if we do a php style argument and take modulo, like, for this particular class of subsets of naturals, it is easy to handle. But but we don't have that this contains an infinite AP of this type. So let's just look at a finite AP, which is inside this and this. You will see the motivation more in a few minutes. But let's just consider such a nice AP, A, 2A, 3A, so on till LA, which is both inside H and inside 1 to N. Then by modular, uh, taking mod A, we have that the elements of A, which are some things, let's say something in this thing, these are elements of A. Among these, at least these many elements must be same mod A by PHP.
Yes.
Okay, so, like, if they let these the elements be C1, C2, C, what should I put? Let's say I. Okay, Ci. These are elements of A with same modulo, which are same modulo A, and I is greater equal this thing. And let's say these are in increasing order. Then
I
can
is
C,
also at most n over al.
yeah, exactly. I is at, so yeah, we'll prove exactly that. So C2 minus C1, what values can it take? Can it be, let's say, can it be A?
No, it can only be greater than LA.
Yeah. So it can't be among these because this is a subset of H. So it is greater equal L times A. Yeah. Then C3 minus C2 is greater equal LA, all the way up to CI minus CI minus 1. From these we get CI minus C1 is greater equal LAI minus 1, which is greater equal because I is greater equal cap, uh like, mod A by A minus 1, which is greater equal L mod A minus LA. Yeah. And if, what is this bounded? Like, what can you
Yes, less than
find
equal to N
here?
minus 1.
Yeah. Let's go with less than equal to N.
Okay.
Then we have this. So L card A is less equal LA plus N. A plus N by L. Yeah. And which is 2N by L. Notice that AL was less than N. A times L was less than n because this was in H and in 1 to n. Thus, L is less than n over A is less than n over L. So this thing. So we have a bound like this, and this is
Okay.
great because okay, what?
Now we need to prove that there is a AP of at least length root n less than equal to n
Yeah,
in H.
yeah. We need to prove there is an AP which is larger than C root n, which has more than C root n values for all n. Because constants don't matter. If we have that, then this is less equal 2 over C root n, like n over root n, and this is just root n. And we are done. Like we just needed to find such a C. So now our main goal is that H intersection 1 2 has a nice AP which is defined as an AP of this type of length L, length is L, greater equal C root n. So any questions till this? So do you see why if we prove this we are done because of this argument? You can type in the chat. Okay, so I'll assume that uh like we are done if we prove this. So any ideas how we might, so first of all, for just for let's forget about n right now. Do you have an idea why H must contain a large AP of this form? Like how
Uh,
can we prove? Okay, yeah.
Maybe we can take the common difference to be a natural number less than 1 by root 2 minus 1.
uh yeah, could you repeat once? Sorry, I did not
Uh,
get that.
like we can write GIF of I root 2 as I plus GIF of I times root 2 minus 1.
Okay, yeah.
Okay. So now we need to find some AP in H, right? So what if we find an like what if we are able to find sequence of I root 2s where the difference between the consecutive i's is constant and force the fractional part to be less than 1 so that GIFs are also in AP.
Yeah, exactly. We do exactly this. So, uh, as Mihir said that if we have if we have small fractional part a root 2, then notice that integer part of a root 2, uh, yeah, if we have small this, yeah, then integer part of a root 2 plus this is a root 2, and thus suppose let's say this is less than 1 by L. Okay, 1 by, I'm using the same notation, you will realize why in a minute. Then we would have that this uh okay, let's call this B. That is not the same as the A that we want. Do you see why this thing is an AP? This is because like the fractional parts add up. Like, yeah. So we have that fractional part of k be root 2 is at most fractional k times fractional part of b root 2. This obvious is this inequality is not hard. Like if this is less than 1, then these are equal, and if greater than 1, then this is obviously less than 1. So less than 1 is less than greater than 1. So, and this is less than k over l. So the integer part of k be root 2 is just uh wait, yeah, so this is just k times integer part of b root 2, because fractional part is equal to, like, if we have this thing, then fractional part equals k times. You can visualize this as uh yeah, if we have b root 2 here, b root 2, then 2b root 2 will be here, and 3b root 2 will be here, and so on, and the fractional parts add up, because, like, because this is less than 1 by l, for example. So so as the so these terms are also in ap, and this is that, like, we have this thing, if k is less than 1 by l. So these things, this is in h, 2b root 2 l, these are all in h, and these form an ap of that type, this also in h, and this is equal this l b root 2. So in particular, if we have that the fractional part of something of this type is very small but positive, then we would, corresponding to this, we would get uh, an ap which is contained inside h.
Actually, now this can be proved easily by a famous result that given any n plus 1 numbers r, 2r, so on, sorry, n numbers r, 2 or n r, there is one number having fractional part less than 1 by n plus 1.
Yeah, we can do it using that directly as well. Okay, yeah. Yes, so, but let's just do this using Pell's equation. So we want to find close approximations to root 2, and note that if let's consider the Pell's equation, this we are taking negative Pell's equation because, like, you'll see in a minute, like, if we consider this, this has solutions x k y k, then x square minus 2y square is minus 1, which means that xk, which means that 2y square minus xk square is 1, which means that yk root 2 minus xk, yk root 2 plus xk is 1. So which means that, and this thing is positive. So let's just bound it by this. Notice that this thing is less than 1 because this thing is greater than 1. So uh, fractional part of yk is equal to this because xk is the integer part of this, the least integer, which is, so that this minus this is less than 1, and hence we have that this is less than. Let's bound this by, let's keep it like this only. So if we consider, okay, we'll bound this by 1 by yk. Yeah, then notice that this thing xk root 2, no, wait, yeah, yk, we want, okay, wait a second, yeah, so we have this thing, no, like, which means that uh this thing, fractional part is less than 1 by like, we have a thing of exactly this type. So in particular, these all the way up to yk, yk, these actually form, this actually is a nice ap which is a subset of h. So any questions till this part?
Can you scroll up?
Okay, here,
uh, a bit more? Yeah, okay.
okay, so any questions?
So above we needed to prove that L is greater than or equal to some C root n, right?
Yeah, we needed l is greater equal 0 10.
Okay.
Okay, so by this, notice that we just need to prove this thing, c root n, so that all of, like, this last term is less than n. We already proved that this does belongs to n, so that less than n. And so if we prove this thing, then this automatically is implied. And let's go with yk less than root n over 2. And so we need to find a yk which is less than root n over 2 and greater than like c root n. So this is easy. Like we automatically got the bound that we wanted. Like, so to construct such a yk, note that we just use the formula like xk plus yk root 2 is 1 plus root 2 power 2k plus 1, and we want this to be less than root n. So we root n over 2. So let's just make this to be less than root n over 2. If we make that, then this would automatically be implied. So take k largest such that plus 3. There exists such a k such that a larger no take a k such that like there exists such a k because of the same thing like this is 2 times k plus 1 plus 1. So this thing 1 plus root 2 power 1 to 1 plus root 2 power 3, this interval union this interval 2 power 5, these all union forms a partition of reals. So for root 10 over 2 we have that like there exists a unique such k, a unique interval in which this belongs, which corresponds to a unique such k. And now we just want uh, a bound, a lower bound of the form c root n on yk, which is found by this. So we have 1 plus root 2 power 2k plus 3, let's say, is greater than root n over 2, which means that, and this is equal to xk plus root 2 yk. And notice that because xk square minus 2y square k square is minus 1, we have that xk is less than, let's say, 2yk. Okay, so yeah, so this is less than,
So that is xk
let's
plus 1
say,
plus root 2 times yk plus 1, right?
yeah, what?
That is xk
Uh,
plus 1 plus root 2 times yk plus 1, right? 1 plus root
yeah,
2 raised to 2k plus 3.
yeah, sorry. Let's write that this 3 plus 2 root 2. Like, I'm factoring out 1 plus root 2 whole squared.
Okay.
Okay, then, and we have that, so we have that root n over 2 is less than 2k plus 3, which equals xk plus root 2 yk times 3 plus 2 root 2, which is less than xk is, let's bound xk by 2 yk. So this is less than 2 plus root 2 yk, 2 plus root 2 3 plus 2 root 2 yk. So yk is greater than root n over 2 times 2 plus root 2 3 plus 2 root 2, and this is all we wanted. Okay, so we are like done. So any
Uh,
questions in this?
Maybe try to wrap up quickly.
Okay, yeah. uh uh so I have written this proof of like existence of uh, a solution to the Pells equation, and I guess you can look at it. So the main idea is the same as Mihir mentioned, that in the interval 0 1, uh, there is this famous result that if alpha is a real irrational number r slash q, then the set of fractional parts uh, is dense in 0 1. In particular, that for any n, we have that there exists a n belongs to 1 2 dot 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 n, such that the fractional part n alpha uh, is either too small or too large, like is we'll use that, is less than 1 by n, or let's say it is greater than 1 minus 1 by n. Yeah, so okay, so you can look at this proof, and then you can also try these problems. Also, there is another thing that for a general Pells equation is an equation of this form, like, yeah. And uh, for this we don't have one fundamental solutions, but we have that there exist finitely many these solutions, such that all solutions are of this type, where z0 is the fundamental solution of this thing. And the idea is that, like, in this you can try to prove this and try to uh, make classes modulo n, so separate them into classes modulo n. Okay, so any questions so far, in so far what we did
What was YK?
in this proof?
Yes.
Okay,
No.
so
Was it the same as the YK that we have defined before?
yeah, it was this equals 1 plus root 2 power 2k plus 1. It was the kth solution of negative Pells equation, which is this, like this thing.
So can you scroll up to the part where you started with the definition of YK in this
Okay,
problem only? No, no. The Can you scroll up the right part? Ah, yeah, that's fine.
okay, yeah, so x square minus 2y square is minus 1 has the kth solution xkyk, and like by this thing we
Yes.
have this.
Yes. So how
Oh,
did you prove that fractional part of YK into root 2 is less than 1 by YK?
okay, that's because let's do so. If xkyk is a solution to negative Pells equation, x square minus 2y square is minus 1, then we have that this thing, which means that we have x uh, 2yk square minus xk square is 1, which means root 2yk minus xk root 2yk plus xk is 1, and which means that 1 over xk plus root 2yk. Thus fractional part, like integer part of root 2yk, is x, because this is defined as the least integer x satisfying this is less than 1, the
Okay, I
greatest
got it.
integers, yeah. Okay,
Okay.
okay. uh, any other questions?
Uh, like this is my first class of this online math club. So are the problems shared on uh,
Hmm.
some
Yeah, I'll
site?
share this PDF with you uh, after the class right now.
Okay, thank you.
Okay, yeah, thanks, like thanks for attending everyone.